All right, so me again. So this talk was born really out of repeated questions around uses of OpenCL on mobile and GPUs in Khronos and other places, and people have encouraged me to come here and talk a bit more about that. Speaker might be dead. Right, about me. So I work as a software architect at ARM, mostly on GPU compute and Mali GPUs, especially. So everything compute, machine learning, you can imagine that gravitates around GPUs. Been participating in the Khronos working group since 2016, so quite a while. OpenCL, Spear, and as an opener, I thought that's a little quiz. Who in the room about ARM? No surprise here. Thank you. About ARM Mali GPUs. Still quite a section. And who programmed an ARM Mali GPU? Much fewer expected. And that's what we often see. And in a way, puzzling because, well, I might surprise you. GPU in the world in number of units. Billions have been shipped, and it's the most pervasive GPU. And that's a fact that often surprises people and is in complete disconnect with the number of people who have touched a Mali GPU. And so granted, here we're talking about compute, and most of the Mali GPUs that have been deployed to date are used for graphics. Slight asterisk to this, but still an interesting discrepancy. So today I thought I'd touch a bit on that and give you very brief history of Mali GPUs. I don't intend to go for death by PowerPoint here. A quick introduction to the architecture of Mali GPUs, mostly the hardware architecture, and then we'll look at how it is used in an embedded space, and some challenge actually that we see for in those spaces. So Mali GPUs, well, it starts obviously before that, but I've highlighted the first date as 2005, and the announcement of the UDGARD architecture by Phalanx, so a Norwegian startup that ARM acquired in 2006, and that formed the basis of what is now our GPU group. Between 2010 and 2015, we've released the MidGuard architecture, unified shaders, grand new concept, and that was using the VLI at the time. So for those who are familiar with that, very large instruction words, you have huge instructions that pack sub-instructions for the various units of the machine. I've linked an article, an Anantic article that does a pretty good job of describing that architecture. This is really old news at this point, so won't dwell on that. 2016 to 2018, then we've made a few releases, the Bifrost architecture around that. So this is maybe a bit more familiar to those who are used to GPUs. And it's a warp engine with thread level parallelism. And once again, I've linked an article that deep dives into the first GPU that was launched for that architecture. And 2019, we released the Valhalla architecture, and also a bit more on that on the next. We're still shipping that architecture. In case you're wondering where names come from, UDGARD, MidGuard, Bifrost, those are all Norse mythology names. And all our code names are based on that, to run out of them, which always surprises me. But if you want to learn more, I've linked the wiki page. That's actually a quite good job of listing all the generations and various features that have been added over time, and the YouTube video as well that are fifth generation of the Valhalla architecture, and this looks like additional GPU. I don't think there's anything surprising at that level of detail for tools with a command stream front end, set stream of commands, very flexible. It's a good fit for modern API. Think Vulkan command buffers, for example, or OpenCL command buffers. They map pretty naturally to that kind of construct. It's got a 16-watt engine, super scalar engine with matrix nothing out of the ordinary, compression technology, FBC tracing, and a whole lot more. not here to give you a sales pitch, really. Looking a bit at the hardware architecture for Alha GPU, I've put it here in the context of a typical platform. You've got your application that talks to the driver using OpenCL or Argonne target the command stream from the GPU. So if we take the example of let's say an OpenCL application that does a queue to the GPU that is translated commands from the command stream front end that further distribute works to the shader cores that we report as compute units in OpenCL speak. Those are all interconnected. I haven't attempted to present that here, and they talk to a shared L2 cache that is the path to so fairly standard architecture, and too surprising here. If we zoom in into, might start getting a bit more specific here. So on the left hand, going into thread creator, it's got many names, but I've picked that one for presentation. That essentially receives blocks of work and split the warp manager that handles the life cycle of a given warp. That's what schedules the warp in and out of the execution engines. And the execution engine can communicate message fabric with a various units. Since we're talking about here of all the units that do graphic stuff, and a lot of them, as you can imagine, a lot of what happens outside of the execution engine is done by a message passing. So as part of the instruction stream, you can send messages to memory access, texturing, I can imagine. And those units have got integrated caches that are, once again, the path to L2 and the memory. The load store unit and texture unit are separate units, so they provide two separate paths to memory. It's actually an interesting thing to observe in program. She can get quite a bit of additional performance by bridging the fact that you have two paths to memory. And the way typically to do that is to use OpenCL images when you can. OpenCL images will read-only images will map to texture units, writable images will map to the load store units. So if you have read-only data, you want to bring that in an image, might be a good idea to get additional bandwidth. What else to say? So the execution engine, if we look more into that, that's got, as you can imagine, lots of sub-engines. You've got an FMA unit that is mostly focused on FMAs and a bunch of other things, special function units, and something handling conversions and various other instructions, subgroups, lane permutations, and all. For a full deep dive here. Yeah, I think that's what I have to say for this one. So maybe before we move on, I'd like to bounce to one of the points about safety critical hardware as well. It's not really the purpose. Those who are interested can go and see on arm.com. We do have fully certified use. So some vendors are pursuing that, and as you might imagine, interesting challenges with it. Happy to talk to you about it if you want to know more. Now, OpenCL in mobile and embedded, that's a question I really often get. People don't have a lot of visibility typically on how OpenCL is used in the mobile and embedded space. And the short answer is that it's really everywhere and in a lot more places than people suspect, really. So when you take your phone and take a picture with it, typically that gets processed with OpenCL on many, many smartphones. It's really not uncommon. And talking about basic processing of it, effects on it, and all that. You'll find OpenCL and Mali GPUs in your electric car as well. That's not something that people might have suspected. In your TV, in your set-top box, processing images. Machine learning, we feel like we're talking just about the uses of machine learning. So you have the fun bunny ears on people's or things like that. That is typically implemented on top of OpenCL. So yeah, it actually is a thing, and it really is everywhere in everyday life. Often it's hidden and it's programmed a smaller number of people maybe compared to desktop platforms. That's why there's less visibility. I've picked some challenges for OpenCL in that space, and use that to trigger maybe some interesting discussions. So as you might imagine, mobile platforms got fairly stringent power constraints, and the power budget on a typical phone is going to be between, let's say, 1 and 3 watts, depending on whether you're looking at sustained workload or something that just peaks for a short amount of time. A fact that might surprise a number of people is that memory bandwidth itself costs power, and to give an order of magnitude, it's about, let's say, 100 milliwatts per gigabyte per second. So if you're consuming 10 gigabytes per second of memory bandwidth, you're already using a watt of power just to get the data in and out of a GPU. And unsurprisingly, that means that compression and all the techniques we can use to reduce the memory bandwidth is quite important to reducing power and getting better battery life and better performance as well on the mobile. Power typically translates to performance. If you consume power at a given operating point, you can clock your GPU higher and run a bit faster. Back to OpenCL and cleanly integrated those image compression technologies, I think will fairly extensive changes to OpenCL. Historically, a lot of control over how images are hardware. Many things have been fairly opaque, and I'm thinking of things like how the data is tiled in memory, how an application can reason about that, or how an application can reason about whether an image is compressed or not. And if we want to introduce all of that to OpenCL, I think we're looking at quite a few extensions. This is work that ARM have started and have been bringing to the group. And I cited a bit earlier some of EXT extensions being developed in the open, and that's what we're trying to do with all of these. So if you're interested in OpenCL images and how that might give you better layers of compression, you might want to have a look at that and give feedback. Really, you don't really know if it's compressed to the handled by the implement. As you might imagine, if you're interrupt entity where it's using technology, it's using